Hi everyone. Today we are wrapping up our statistics unit that covers normally distributed data, the normal curve. And we're going to do this by talking about how to find different areas underneath the curve. Now that may sound similar to what we did when we did the empirical rule, and it is similar, but the empirical rule is a little bit restricted in that it only works if you're on exact numbers of standard deviations. So if you go one standard deviation out, two standard deviations out. Today we're going to talk about how to find areas in between those standard deviations. Okay, it is going to rely heavily on the use of a graphing calculator. So if you do not have your graphing calculator handy, you may want to pause the video right now and get it. If you don't have a graphing calculator at home, we did put out a list of online options. So I would fire one of those things up and be ready to go. Okay. Okay, so we're going to start out with this example one where it talks about just a normal distribution, and I think you've actually looked at this distribution before. The height of American men is approximately normal with a mean of 69 inches and a standard deviation of 2.5. So we're going to start by just drawing our normal distribution. So there's your normal distribution that you know and love, okay? And you should know those percentages pretty well by this point. So when I ask you a question about what percentage of men are over 74 inches tall, we can say, all right, well, here's 74. The area to the right, or the percentages to the right, would be the 2.35 plus the 0.15, and we would say 2.5%. Okay, that represents this area right here. Okay, and that's all fine and good if the number that I ask you about shows up down here, right? But when we go down here and I say what percentage of men are just over 6 feet tall, over 72 inches tall, then we're going to have a little bit of a problem. We can see 71.5, so we might be able to give a decent estimate. But if I actually wanted to know where 72 inches would fall, I would have to drop a line down there that is not already there. So 72 inches might be somewhere like here. Okay, and again, we could probably give a decent estimate for that, but we don't know an exact value until now. So what we're going to use is a function on our calculator called normal CDF. And I'll show you where to find it in just a second. But for normal CDF, you need 4 pieces of information. You need the lower bound and the upper bound. You need the mean, and you need the standard deviation. Okay, so let's talk lower bound, upper bound. We're looking for this area right here. Okay, so the lower bound of our region that we're looking for the area for is 72 inches. Now, if we want everything above 72 inches, really our upper bound is infinity. Okay, so I'm going to put that down, but then we're going to talk about how we're going to enter that into our calculator. We want to know, I mean, even if this person is way above 72 inches, we want them included, right? So we want to go from 72 out to infinity. We want to know what percentage of men fall into that category. Mean and standard deviation were given in the problem, right? So 69 and 2.5. So in my calculator, what I'm going to do is I'm going to go to the menu that says distribution, which is up above the variables key. You'll see DISTR. So second, distribution. And the option I'm looking for here is number 2. Okay. So I'm going to do normal CDF, and then I'm typing the numbers in this order. It's lower bound, upper bound, mean, standard deviation, every single time. So lower bound is 72, and then I'm going to put a comma, okay? Upper bound, by the way, newer calculators might not look like this. Newer calculators might have it like laid out for you like 4 different things you have to fill in. You might not have to use the commas. So, but you're still going to follow everything else the same way we're going to do. Now, for infinity, your calculator doesn't have a way to process infinity. But if we just put a really gigantic number on here, like something that's almost impossible as a height, your calculator is going to be able to figure it out. Because remember, this curve keeps approaching that x-axis, right? It's going to get down to a probability of almost 0. So we could just every time try to make up a number that we think is big enough, But what we're going to do instead is we're going to use 1E99. Okay, 1E99 is your way of communicating infinity to your calculator. That's 1 times 10 to the 99th power, or a 1 with 99 zeros after it. I think that's the biggest number your calculator can process, so that's why we use it for infinity. Okay, by the way, I got there by doing 1, and then the EE is above the comma there, so 1EE99. Okay, that's how you do infinity, comma, 69, comma, 2.5. Close your parentheses, hit enter, and there's your answer. Okay, we would put this down, we're putting this down as a percentage, so I would probably say something like 11.5% of men are above 72 inches. Okay, I like to draw the normal curve still, just to get an idea of what kind of area I'm looking for, because if my line was way over here, and I was shading this way, and I got an answer like 11.5%, I would know that that answer didn't really make sense. So I like to still have a visual. Okay? All right, so let's try our next one here. Next one wants to know what percentage are between 5.5 or 5'5" and 6 feet tall. I'm going to convert these all to inches because I'm going to need inches to work with up here. So 5 feet is 60 inches plus 5, so this is 65 inches. And 6 feet tall would be 72 inches. And again, I like to put these on my normal curve just so I can get an idea of what this is going to look like. So let's see, 65 is going to be somewhere in here. And 72, we just said, is that purple line. So it's going to be this big bulk. I'm expecting this to be a fairly large number, right? At least 68%, okay, should be larger than 68% just for reference. So this is what I'm putting into my calculator, and I am going to ask on your homework that you please write this part out along with your answer so I can see what you put into your calculator. So norm CDF, lower bound would be 65, upper bound would be 72, my mean, and my standard deviation. So you can put it in exactly how you're typing it into your calculator. Okay, in my calculator, I'm in distributions, normal CDF, okay, and then I'm typing 65, 72, 69, 2.5. Okay, remember that estimate. Let's make sure we're close. Oh, 83% sounds pretty good. So I would say 83% of men are between 5'5" and 6 feet tall. Okay, so that's what normal CDF does for us. It gives us an idea of areas under the curve that don't fall exactly on those standard deviation lines. Okay, let's try the next example. All right, so Joan found that her average phone call was 9.6 minutes with a standard deviation of 2.4. We know that her phone usage was roughly normal. Don't ask me how we know that it's normal because we would have to do a lot of data collection for that. But what percentage of her calls fell into these categories? Okay, so like I said, I usually like to start by drawing the normal curve, even though I don't technically have to. So what percentage of her calls were less than 5 minutes? What I'm putting into my calculator here is norm CDF. By the way, norm CDF only works when we know that we're working with normal distributions. Norm CDF, lower bound, so this time we want to go up to 5 minutes. So 5 minutes is like here, and so I want this area. My lower bound here is negative infinity. So in my calculator, I'm doing negative 1E99. Upper bound would be the 5 minutes. Mean is 9.6. And standard deviation is 2.4. Distributions, norm CDF, type it in. 5, 9.6, 2.4. Nope. And we are expecting this to be a fairly small amount. I mean, up to that standard deviation line we know is 2.5%. So 2.7%, and really if I was rounding, this would be 2.8%. Seems reasonable to me. Okay, less than 10 minutes, so same thing. So up to 10 minutes. Now 10 minutes, let's see. Let's switch colors here a little bit. 10 minutes is going to be here, right? So that goes all the way up. I'm expecting this to be more than 50%, right? If the mean was 9.6. So watch this. We can hit second enter and bring that whole chain back up, and then all I really have to do is change that 5 to a 10. Not sure how that's going to work on the newer calculators. I am having to use insert here to get that 0 in there. Okay, so I'm not over typing anything else. And I get 56.6%, which again makes sense to me based on my drawing. Okay, more than 15 minutes. So let's see, 15 minutes is going to be somewhere over here. So again, we're expecting this to be small. This should be even smaller, I believe, than the less than 5 minutes. It should be even smaller than the 2.8 because it's not even 2 standard deviations. So we're going to do norm CDF. This time, the 15 minutes is our lower boundary, right? Upper boundary is infinity, 9.6 and 2.4. And let's see, I'm doing 15 minutes up to infinity, 9.6, 2.4, and I end up with 1.2%. Notice I'm moving the decimal point on all of these because they're all percentages. Okay. And between 4 and 8 minutes, the only change I'm going to make there is I'm going to set my lower and upper boundaries to 4 and 8. 4, 8, delete everything else. There we go. Oh, and I forgot to draw that on our chart, but 24.3%, I would say. Okay, so one more thing we need to talk about in terms of using the functions on our calculator. This is when I give you the data points that fall down below and you're looking for the percentages. What if I give you a percentage and ask you where that data point falls? That's what this next question is focusing on. So selection of movies from Family Video are roughly normal. So we took a random sample, we figured out how long all the movies were, looked at that data set, and it was normally distributed. Average length of 2 hours, 3 minutes with a standard deviation of 17.25 minutes. I'm going to start right away by turning this all into minutes because otherwise this is not going to work well together. So this is 120 minutes plus 3, so I'm just making this 123 minutes as my mean. Okay, and I want to know what is the 84th percentile. So if I think about my normal curve, and I'm not necessarily going to label the entire thing this time, but if I drop a line at a point where 84% of the data is to the left of that line. That's what percentile means. What is this number right here? I want to know what length would I have to be longer than 84% of the data. And so to answer a question like this one, we're using a different function, still in that distributions menu. It is called inverse norm. Okay. And the inverse norm function is developed to help you find the data point that corresponds with a percentage to the left. Okay. It's important that you know it's always the percentage to the left because sometimes I'm going to ask you to do to the right, and there's going to be some other things that we have to worry about when we do that. We're going to have to do some conversions and things like that. Okay. But this one should work just fine. So 84th percentile, what I'm typing into my calculator is inverse norm. Okay. And you give the percentage as a decimal. So I'm doing 0.84. And then just like before, we're going to give the mean and the standard deviation. And that will tell you what data point you would have to be at 84%. Now remember our mean was 123, and so that would be 50%. So I'm definitely expecting it to be something larger than 123. I'm going to go to my distribution menu again, and you should see that next option down, inverse norm. Okay, we're going to type in 0.84, 123, 17.25. Okay, and it gives me 140-ish minutes, which in terms of our normal curve makes sense. Okay, so these next two questions are very similar. Okay, so I'm just going to do second enter, and I'm going to change my 0.84 to a 0.90. Okay, and I get 145 minutes. Okay, and then I'm going to do the same thing, except I'm going to change this to a 0.99, and it is important to get that third 9 in there, so I used insert to do that. And I get 176 minutes. Now, that might throw you off a little bit, because look at the distance between 84th and 90th, and look at the distance between 90th and 99th. Like, there was a huge jump there, right? Remember how slow and small this curve is by the time it gets out to the 99.9th percentile, okay? It's got to travel kind of a long distance horizontally to add on that extra percentage when it gets that low to the axis. So just keep in mind, like, the difference between the 99th percentile even and the 99.9th is probably pretty big. Let's take a look at that real quick. If I deleted one of those 9s, remember I said that was important, and just did the 99th percentile, that would be 163 as opposed to 176. So even that extra 0.9 traveled quite a distance on a normal curve when you're way out at the ends like that. Okay, third percentile is going to be way down here. I just want to know, where would I have to be where only 3% was to the left of me, right? So we're going to do inverse norm. 3% would be 0.03, and then the 123 and the 17.25. Okay. So I'll change that to 0.03, and that would be 90. I guess we could round this to 91 minutes. I'm following my rounding rules. Okay, and we expected that to be smaller, significantly smaller, right, than the 123. So that makes sense to me that that would be about 90 minutes. Okay, before we move on to that next question, I wanted to do one other type of question that I didn't include in this example, but it's important. And I sort of referenced it up here when I talked about inverse norm always referring to the percentage to the left. Let's suppose I had asked you about the top 3% of the data. I want to know, where would I have to draw my line to wall off the top 3% of the longest movies that Family Video has, okay? So the big mistake that I see people make is they type it in as a 0.03. But let's keep in mind, we typed in a 0.03 here for our third percentile, and that was way down here. So when you're dealing with these questions that deal with the top data, what you have to keep in mind is, if you are looking for 3% data over here, and this is the data line you want, in order to use inverse norm, we have to think about what data is to the left of that line, not what data is to the right. So not like this is hard math to do, but we have to remember to do it. That if I'm looking for the top 3%, I do not want to put in 0.03, because that's going to give me some number way over here. In fact, we already know it's going to give us 91, and we do not know that we know that the top 3% are not 91 minutes long. Okay, the bottom 3% are. So we want to think of this as 97% is the data to the left of that line we're looking for. So anytime you're dealing with one that's asking you about the top of a data set, you have to remember to subtract from 100%. Okay, and so what I'm actually going to put in here is inverse norm of 0.97, and then my 123 and 17.25. Okay, so let's see. Oh, I cleared my screen here. Distributions, inverse norm, 0.97, 123, 17.25. and I end up with 155. Which makes sense to me, right? That 155, the 97th percentile, is going to fall between 90 and 99.9. So the top 3% would be somewhere in here. Keep in mind the 90th percentile represents the top 10%. The 99.9th percentile represents the top 0.1%. Okay? So just wanted to make sure we did one where you dealt with the top percentage, and now we'll talk about that middle 15%. Okay, so that takes us to this question, the middle 15%. Okay, so what we want to do is we want to figure out what percentage would these lines have to be at to have 15% of the data in between them. Okay, I need to know what percentage is this and what percentage is this. Okay, and if we're going for the middle, we're going to start from the mean. So let me draw a diagram here for you. If my mean is considered to be 50% of my data, notice I'm not even labeling what the actual mean is right now. I'm just saying this is 50%, and I want the middle 15, then I want to go half of 15 off of 50 in each direction. So I want to go 7.5% in each direction from the 50. And that will give me a total of 15% in the middle. Hopefully that makes sense. If not, rewind it, listen to it again. That if I go 7.5% from 50 this way and 7.5% from 50 this way, then I'll have my middle 15 because this makes 15 total. So 7.5 backwards from 50 would be 42.5%. And 7.5 forward from 50 would be 57.5%. Now I need to figure out what are these data values that correspond with those two percentages. Okay, and again, I'm talking about data to the left. So this line represents 42.5% of the data over here. This line represents 57.5% of the data over here. So what I have to do to answer this question is I actually have to do a double inverse norm. I have to do the process twice. And my answer will be between these two values. So let's see, inverse norm 0.425. So that's 119 minutes. I guess 120 if I'm rounding. And do the same thing with the 0.575. It took me longer to explain that question than it was to actually do it. And that would be 126 minutes. So my middle 15% would be anything between 120 and 126. That's how I would answer that question. Okay, so you got a lot of practice with your calculator today. Do keep in mind that on your homework assignments, I do want to see these setups. That's why I was so adamant about writing them out every single time. All the questions should kind of fall in line with what you're seeing here as examples. All right, good luck to you.